I now want to compare with you the results that we have for the spring with the results that we have from the pendulum to give you some further insight. We have the string and we have the pendulum. And I'm only going to look at the period t, which here is 2 pi divided by the square root of m over k, and here is 2 pi times the square root of L over G. If I look here, there is a mass in here. If I look here, it's independent of the mass. Why is there a mass in here? That is very easy to see. If I take a spring and I extend the spring over a certain distance, then there is a certain force that I feel. That force is independent of the mass that I put at the end of the spring. The spring doesn't know what the mass is you're going to put on. All it knows is I am too long and I want to go back to equilibrium. That force is a fixed force. If I double the mass, that fixed force will give, on double the mass, half the acceleration. If the acceleration goes down, the period of oscillation goes up. It's very clear. So you can immediately see that with a spring, the mass must enter into the period. Now go to the pendulum. If I double the mass of my bob at the end of a pendulum, then the vertical component of the tension will also double. That means this restoring force, which is proportional with the tension, will also double. So now the restoring force doubles, and the mass doubles, the acceleration remains the same, the period remains the same. So you can simply argue that there should be no mass in here, and there isn't. How about this K? If K is high, then a spring is stiff. What does that mean, a stiff spring? It means that if I give it a small extension, that the spring force is huge. If I have a huge spring force, the acceleration on a given mass will be high. If I have a high acceleration, the period will be short. And that's exactly what you see. If K is high, the period will be short. G. Imagine that you have a pendulum in outer space, that there's no gravity, nothing. The pendulum will not swing. The period of the pendulum will be infinitely long. Go into the shuttle, where the perceived gravity in their frame of reference, perceived, they're weightless, remember? Their perceived gravity is 0. You take a pendulum in the shuttle and you put it at this angle, you let it go, it will stay there forever and ever and ever. The period is infinitely long. But take a spring in the shuttle and let the spring oscillate, and it does. So you can actually measure the mass of an object using a spring on the shuttle and let it oscillate if you know the spring constant. And that's the way it's actually done. So you see indeed that these things make sense when you think about it in a rational way. We have here in 26100 the mother of all pendulums. It is a pendulum, oops. It is a pendulum which is 5.1 meters long, and there is a mass at the end of it which is 15 kilograms. The length is 5.18 meters, and the uncertainty is about 5 centimeters. We can't measure it any better. And the mass at the end of it, which doesn't enter into the period, is about 15 kilograms. The period, which is 2 pi times the square root of L over G, if you substitute in your length of 5.1 meters, you will find 4.57 seconds. 4.57. Since you have a 1% error in L, you're going to have a 0.5% error in your period, so that is about 0.02 seconds. So this is my prediction. And now I'm going to oscillate it for you, and I'm going to do it from 2 different angles. I'm going to do it at a 5-degree angle, and I'm going to do it at a 10-degree angle. In order to get my relative error down I will oscillate 10 times. So I'm going to get, at an angle theta maximum of roughly 5 degrees, I get 10t equals something plus or minus my reaction time, which is 0.1 of a second. And then I will do it from 10 degrees, and I will do again 10t, and again my reaction time is not much better than 0.1 seconds. So let's do that first. I will move this out of the way, because if that 15 kilogram object hits this, that is not funny. All right, 0. I have a mark here on the floor. This is about 5 degrees, and this is about 10 degrees. I will first do it from 5 degrees. I will let it swing one oscillation, and when it comes to a halt here, I will start the timer. That's for me the easiest. But I count on you where it comes to counting. You ready? You ready? You sure? I'm ready too. Okay. Now keep counting, and don't confuse me again now. You're completely responsible for the counting. So all you have to tell me is when 8 or 9 is coming up. That's all I want to know. Don't even bother me with 3. Don't even bother me with 4. Just let me know when I have to get in position for the final kill. Notice there's almost no damping on this pendulum. The amplitude remains almost the same. Whereas with the air track, you could actually see that there was already some kind of friction. It was, where are we now? 9? 9, right? 45.70. 45.70, where's my chalk? 45.70. What was my prediction? Yeah, exactly. You get the picture. That is pure luck, because my accuracy is no better than a tenth of a second. Now we do from 10 degrees. And I want to show you now that the effect on the angle, when you go from 5 to 10, is small. So small that you cannot measure it within the accuracy of your measurement. Yeah! Okay. Again, relax and count. Ah, nerve-wracking. Ooh. Where are we now? 7. Did you expect anything else? 45.75. One of the most remarkable things I just mentioned to you is that the period of the oscillations is independent of the mass of the object. That would mean if I join the bob and I swing down with the bob, that you should get that same period. Or should you not? I'm asking you a question before we do this awful experiment. Would the period come out to be the same or not? Some of you think it's the same. Have you thought about it, that I'm a little bit taller than this object, and that therefore maybe effectively the length of the string has become a little less? If I sit up like this, and if the length of the string is a little less, the period would be a little shorter. Yeah? Be prepared for that. On the other hand, I'm also well, I'm not quite prepared for it. I will try to hold my body as horizontal as I possibly can in order to be at the same level as the bob. I will start when I come to a halt here. There we go. Now, you count. This hurts. Ah. I want to hear you loud. Oh. Ah, thank you. Oh. T with Walter Lewin. 45.6 plus or minus 0.1 seconds. Physics works, I'm telling you. I'll see you Monday. Have a good weekend.